Wait, oh yeah, Max is 21, 5 days. Yeah, there's a group chat for lunch. So you both of them also. And she didn't say nothing yet. Yeah. Guys, what do you guys think?
All right. Let's see. People on Teams, can you guys hear me okay?
Yeah.
Thank you. So on today's links, there are two worksheets. This is from last Friday that we're going to do with similar triangles. And then off of the other printout or the other link is this worksheet here. It has linear approximation, L'Hopital's rule, and those are the other two topics that I wanted to go over today. Okay. And then tomorrow we'll do our full test review. Wednesday we'll continue reviewing this day, and I'll have a morning session on Wednesday, and then Thursday is your test. All right, so I'm going to read the problem, and then we've seen similar triangles already with cones, but these shadow problems are very specific to these types of problems, or to this, the setup for this is very specific, and it's, but then once you see it, you're going to see it's easier than cones, even though they both involve similar triangles. All right, so let me read the problem here. A man who is 6 feet tall is walking away from a lamppost at a rate of 5 feet per minute. So here's the man, 6 feet tall, represented by this height of the small triangle. Walking away from the lamppost at a rate of 5 feet per minute. We'll come back and see where that plays a role in our equation. Lamppost is 20 feet tall, so that's represented here. Person casts a shadow on the ground in front of them. So y is the length of the shadow here. So you can imagine that as the person's either walking towards or away, that length of the shadow is going to be increasing or decreasing depending on, right? So here's the light source. As the person is walking towards the lamppost, the shadow length is going to decrease. As he walks away, that shadow length is going to be increasing. Okay, how fast is the shadow growing when the person is 30 feet from the lamppost? We need to figure that out. And also part B, how fast is the tip of the shadow moving when the person is 30 feet from the lamppost? So tip of the shadow, how fast the tip is moving in relation to the ground. But initially, we're just going to create proportions using the diagram that we have in front of us. So we do similar triangles because we have a triangle within a larger triangle, and they both share some initial information here. Okay, so this is how we can start. We can say the height of the small triangle is to the height of the large triangle. So I can say 6/20 as the base of the small triangle. So what can I use to represent the base of the small triangle? Y, okay. Is to the base of the large triangle. What's the base of the large triangle? Okay, involves x and y, but how do we write that? X plus y, yeah. So we want to make sure that we add the two rates together, add the two values together to get the full length, right? We don't want to do x times y. And also based on the pattern, some students want to write x over x plus y. But the way that I've drawn this diagram, the x is not the full length of any base. It's actually y that's represented the full base of the smaller triangle. So it's easier than cones because we don't have to worry about substituting with another equation. This is the only equation we got to deal with. So there's not a separate equation we got to substitute and clean up and reduce. We just have to work with this equation. So I can deal with this a little bit easier if I can get rid of the denominator. So I'm going to cross multiply here. So I'll distribute the 6 through. Combine like terms. So I'm going to bring the y over to the right side. And we're ready for the derivative. So we need to find the derivative of 6x, find the derivative of 14y. All right, so what does 6x turn into? Remember, time is still impacting every variable here. So 6x becomes times what? Yeah, dx dt, yeah. All right, 14y becomes, yeah, 14, good, dy over dt. So that's really the only calculus in this problem. We're just going from here to here. It's a relatively easy step, right? Okay, so we'll come back to it. Well, let's go back to the, before we go back to the problem, actually, let me define some of these information that's coming out of the derivative. So dx dt is how fast that x is changing. So this x is changing depending on how fast the person is moving, right? So we say dx dt is the rate of the person walking. So either he's walking away or he's walking towards the lamppost. So if he's walking away from the lamppost, what do you expect your rate to be? Positive or negative? Positive, because x is getting longer, right? Okay. What if he's walking towards a lamppost? Negative.
Negative.
Yeah, because x is getting smaller, so it's not the direction, right? The direction moving left or right has nothing to do with it. It's what's happening to the sides of our dimension. So negative. Good. Now dy dt, this represents how fast y is changing, and y represents the shadow length. And finally, the tip of the shadow. If you can imagine the tip of the shadow, we're basically seeing how fast that point is moving on the ground. And that point on the ground is going to be dependent on how fast the person is walking, but then also how fast the length of the shadow is increasing. So both these speeds is going to impact how fast that tip of the shadow is moving on the ground. So that tip of the shadow is going to be just, we add the two rates together. How fast the person is walking, and also on top of how fast that shadow length is increasing because of the fact that the light source is causing that shadow length to increase or decrease. Okay, so let's go back to the problem here and see if we can assign some values here. Man who is 6 feet tall, okay, we already have that in our diagram. He's walking away from the lamppost at a rate of 5 feet per minute. So what can we assign that? What variable is that going to represent? Okay, dx over dt. Walking away. All right, any questions so far? Okay. Keep reading here. Let's see, lamp post is 20 feet tall. We already have that information. Person casts a shadow on the ground. Okay. How fast is the shadow growing? Okay. So what are we looking for? What variable is that talking about? Yep, dy dt, right? Shadow length increasing is, or decreasing is dy dt. So that's the missing information that we're after. When the person is 30 feet from the lamppost. What can we assign 30 to? X, yeah. All right, distance to the lamppost, 30 feet, okay. So we're solving for dy dt. Here's our equation, and I think we have enough information, right? Plug in 5 for dx dt, and we're ready to solve for dy dt. So let's do that. Okay, divide both sides by 14. Reduce that fraction. And units is still feet per minute, right? All right, that's part A. Part B, how fast is the tip of the shadow moving? So we have a formula for that, right? We just add the two rates together. The tip of the shadow is based off of the person's speed and the shadow's increase. So we just total them together. So rate of change of the tip is 5 plus 15 over 7. Okay, any questions? So look at what we did. Was there any piece of information that we didn't need that they gave us? Or is there a piece of information that we just didn't use, that we didn't have to use? Yeah, that 30. And why do we not have to use that 30? Okay. Yeah, our relationship for our derivative doesn't include x. So that tells us that it doesn't matter how far he's standing away from the lamppost. It could be 10 feet away, it could be 5 feet away, it could be 30 feet away. It's not going to impact the rate of change of the speed of the person or the shadow length. So usually this doesn't happen with problems where they give you extraneous information, but for this type of problem, somehow it does. And AP exam, if it shows up, at least you can recognize that there's a piece of information that potentially we don't use. All right, any questions? All right, so I want you guys to feel comfortable with this type of problem. So can you guys try number 2? Give you guys a few minutes to try this problem. Same scenario, same diagram, just different numbers, and maybe there's a slight change in the rate. But if you guys can use number 1 to kind of help you through the problem, then at least kind of gives you more confidence that this type of problem you're good with. Okay, so spend a minute, and then I'll go over it with you. Okay, let's check how your setup looks. Notice that the person is walking towards the lamppost, so we have to make that adjustment, right? dxdt is now negative. Okay, so we create our diagram here. We can say 5 is to 15 as y is to x plus y, cross multiply. You can reduce however way you want to. Either way, we should be able to get it down to 2y equals x. Okay, we find our derivative. Y becomes dy dt, x becomes dx dt, and then we just plug in, right? Oh, I think for this problem, I think B is probably the first one you want to solve for, right? Get that shadow length first, and then for part A, then you can, I should have flipped this around. Then we can add the two rays together. So shadow length is negative 2.5 feet per second. And then the tip is adding the two rays together, so negative 7.5. All right, any questions? Okay. I do want to come back to the back page. I want to go over cylinders since it's similar to cones, but it's easier. But let's go to the other handout because I want to go over linear approximation and then L'Hopital's rule. All right, no questions here? All right, let's flip over to the other handout. So it says linear approximation and L'Hopital's rule up top. We already did this top portion here. So let's go to this linear approximation portion. Okay, so let me read this out here. Linear approximation is approximating the nearby y value on the graph using the tangent line equation. So I want to show you that you already know how to do most of it. Okay, because the emphasis is going to be on the line. So the first thing we do is finding that tangent line equation. So we knew how to we learned how to do this from chapter 2, right? So find the order pair, find the derivative, from the derivative find the slope, create your tangent line equation. Okay. And then the one new thing that we have to do is this approximation portion. And it's easy. All we do is we just plug the decimal in. Whatever decimal they provide, just plug it into the tangent line equation. So this process looks intimidating, that those two words together, linear approximation. So, but all we're doing is we're taking that line that we know how to find. The approximation is just whatever decimal they give you, just plug that decimal into that line. All right, let me kind of show you the visual process behind this. So let's say we had a curve, and let's say that curve was f of x. A point is going to be identified for us, and then from that point, we're going to find the order pair. From that order pair, we're going to find the derivative. From the derivative, find the slope, and we get to our tangent line equation. So let's say we create this tangent line equation that's going to skim the surface of the graph at that point. So the whole idea with linear approximation is that if we pick a point that is close to this point, then our approximation is going to be pretty good, right? Because as long as we're close to that point, I mean, it's not going to be the exact value, but a point on this line is going to be close to the point on this curve, right? Value-wise, the y value is going to be pretty close. Now, if we veer farther and farther away from that point, then our graph is going to become less and less accurate. Okay? But as long as we're picking a decimal value that is within a certain range, then our approximation will be pretty good. So you're going to see that the decimal values that you're going to be asked to approximate are going to be close to that point. So let's look at number 2, but I'm going to phrase number 2 in a way that is easier to hopefully understand, and also this will be the case on your test as well, so it won't be phrased like this. Cross that out. So let's write it this way. So given that our function is square root of x, we're going to approximate y of 9.2 when x equals 9. Okay, we're going to ignore this statement to begin with. We're just going to focus our attention here because 95% of our work can just be done by using this information. So we're going to find the order pair, we're going to find the derivative, we're going to find the slope, we're going to create our tangent line equation, and then our final step, we can plug that decimal in for x. So let's gather some information first. How can I find the order pair? How can I find the point? Yep, we just use the original function, right? Use the 9, plug into the function, get the y value. Which is equal to 3. Okay. To find the slope, I need to find the derivative, but to find the derivative, what cleanup do we have to do? Let's rewrite this as what? To get it ready for power rule.
X to the 1/2.
X to the 1/2. Okay, so then if we go through power rule, we can find the derivative, and if we find the derivative, then we have a slope formula to work with, right? Okay, f prime. What's the derivative here?
1/2 x to the 1/2.
Good. So 1/2 x to the negative 1/2. I can clean that up, bring that down. You can put the square root, that's fine. I'm going to leave it as x to the 1/2, but square root is definitely okay in your final answer. So now that we have our slope formula, what can we do next? Yeah, well, let's find the slope first, right? So the 9, we can plug into the derivative to find our slope. Again, we're ignoring this decimal, right? This is the final step. We're not going to use this at all, not until the very end. All right, let's clean that up. What is that slope going to clean up to be? Good. All right, square root of 9 is just 3. 2 times 3 is 6. So we have enough information to create our tangent line equation, right? We got the order pair, we got the slope. I'll put this down here, y minus 3. Okay. Nothing new so far, right? We know how to do this. I'm going to move that 3 over just to get it ready for my eventual plugging in. So I'm just going to move that 3 over just to make it a little bit cleaner. So get that y by itself. All right, everything up to this point is a review, right? So we took care of the linear portion of this problem. Now comes the approximation. So we're just taking that decimal value and putting it in for the x. And whatever the calculator gives us, that's our answer. So if you know how to find tangent on equation, this should not feel like it's very difficult. Yes, question.
So why did you go from +3 to -3?
Oh, I just want to get that y by itself.
Oh,
I
okay.
just moved that 3 over just to make it easier for my final step, because my final step, I just want to enter all this in my calculator.
Okay.
Yeah. So the big point I want to get across here is this should be easy, right? But sometimes when you see that linear approximation, it just throws students off and they don't know how to get started. But if you just get that tangent line equation and then just plug that decimal in, then that's all there is to it. Yes. Oh, sorry, I messed up. This should be +3, right? My bad. That's not a mistake. Is that what we were asking?
yeah, no,
Sorry,
no,
my
no.
bad, my bad. I thought you were asking about this
realize
stuff.
that.
Thanks for bringing that up. Yeah, that -3 +3, but I just didn't carry that down. I miscopied it. Did you guys get this answer though? 3.033. Okay. Okay, any questions about the process? Can we go to, so I want us to practice this problem, this process. Let's go to example 3. I'm going to reword the problem for example 3, and then have you guys try this step, or try the process. So here's example 3 on the back. Everybody good with this? Okay, here's 3. So cross that out, and then in place of it, I'll reword it this way. We have our function, our curve is y equals cube root of x. We approximate a decimal. That decimal is going to be close to our point of tangency, but we don't care about the -8.1, right? You're just going to focus your attention on just these pieces of information. So follow the steps that we did with 1. Use that to kind of help you with your steps. Let's see how far we can get. Okay, let's see your progress so far. So there's my ordered pair, there's my slope. And then point slope, and then final step is the decimal. Okay, just like before, we use the ordered pair, or we use the original function to get our ordered pair. We found the derivative by first rewriting the radical as a rational exponent. Power rule. Use the derivative to find our slope. So after that, we take our ordered pair. Okay, we take our slope. Point slope form, tangent line equation, bring the two over, and then decimal. All right, any questions here? Okay, one more topic, and that is L'Hopital's rule. It's right below that. So we're gonna revisit limits here. Do you remember with limits we talked about how we always, if we see a real number, we always plug in that real number? We have a different set of rules for infinity, but for real numbers we always plug in, and then from there we can make our next decision, right? We talked about how if we get 0 over 0, we know that there's a hole in the graph. If there's a hole in the graph, we know the limit exists. We just have to kind of figure out what that limit is. And we learned from chapter 1 that we had a couple of ways to get that hole to cancel out, right? Either through factoring, through conjugate method, through simplifying complex fractions. But either way, we had all these algebraic steps available to reduce and reevaluate. But now we're going to take advantage of what we learned with derivatives and give us another option for dealing with limits, or limit that has 0 over 0. So rather than going through potentially messy steps to have to factor, reduce, we can just find the derivative, and that sometimes can either speed up the process or it can allow us to solve for problems that otherwise would be difficult to do algebraically. So this gives us another option to handle limit problems that we didn't learn in chapter 1 because we hadn't learned about derivatives yet. But now that we've learned derivatives, we can go back and we can speed up the process for some of these limit problems. So here's what we do. If you get, but remember the first thing you got to do is we got to get that 0 over 0. Okay, we can't do this L'Hopital's rule unless you first get 0 over 0. So the first step from unit 1 didn't change. Okay, we still always plug in that x value because we have to gather information before we can decide what to do. So if we get 0 over 0, that will give us the license to find the derivative of the top portion and then find the derivative of the bottom portion separately. So the numerator, we go through power rule, we find the derivative. Denominator, we go through power rule, we find the derivative. And we have just f prime over g prime. Once you have your derivative notation, you've created a simpler version of the problem that you can now reevaluate with the limit. And this will give us the same answer as if we were to factor, reduce, and reevaluate. Okay, a couple things I want to bring up. The f prime over g prime, this doesn't take the place of quotient rule, right? Quotient rule is if we want to find the derivative of a function that has a numerator and denominator. This is just serving the purpose of finding the limit. Okay, so I don't want us to do this f prime over g prime if if I gave you a function that requires quotient rule. But we're doing this just specifically to handle limits. So once you have derivative of the top and bottom, you're going to plug in or re-plug in your x value and see if that will get you down to a real number. All right, so let's practice our process, and we're also kind of reviewing our limit steps from Unit 1. So let's skip down to number 6. Maybe it's a little tough for you to read if you don't have this in front of you. But I'm just going to walk us through it. This is a messy expression, numerator and denominator. But the first thing we do is we have to plug in that 2. So if we plug that 2 in, we use our calculator. The numerator and denominator, if we plug in, just to speed up the process, it does produce 0 over 0 for us. So write it bigger here. So if we get 0 over 0, from Unit 1, we knew that we could look to factor GCF, but it's a little messy to do that. So we're going to practice going through L'Hopital's rule because we have the license to. We have 0 over 0, so that gives us that ability now to handle using L'Hopital's rule. So we're going to take the derivative of the top, and then separately, we're going to find the derivative of the bottom. So these are big numbers, but I think power rule, we should be able to handle it pretty easily here, right? So what's the derivative of 105x squared? Yeah, 210x. 420x becomes just 420. The constant goes away to 0, so we can drop that out. Denominator, we're also going to find this here. So we went through L'Hopital's rule. We have a cleaner version of the problem. And what's our next step? Yeah, let's plug in the 2, right? Plug in the 2. Let's see what we get. Maybe if we get a real number, we can stop. But if we get something else, we may have to look to see how we can continue the problem. All right, we plug 2 in, and what do we get? Top. Yeah. Denominator? It's also 0. So we get another variation of 0, 0, 0 over 0. So that gives us the chance to do L'Hopital's rule again. So we're going to find the derivative once again. And what does 210x become? Just 210. Constant goes away to 0. And then the denominator, 216x. 216. Again, the constant goes away. Now, technically, we should be reevaluating, but there's no more variables to reevaluate, so this is our answer. But we can further reduce. You can use a calculator to reduce that fraction. Okay. So a couple of things I want to point out with L'Hopital's rule. First, it's not the same thing as quotient rule, right? We don't do this if we have a numerator and denominator, if I ask you to find the derivative. It's only for limits. And we always have to plug in, right? We can't just assume L'Hopital's rule, just find the derivative without first confirming we're getting 0 over 0. So each time you get a 0 over 0, that means you have it gives you a license to do L'Hopital's rule once. Okay, and as soon as you do L'Hopital's rule once, you got to reevaluate. Sometimes we want to do this. Sometimes we want to keep finding the derivative until we get constants, and then we have that as our answer. In this case, that's true. But on the test or on the quiz, sorry, on the test, if you're doing L'Hopital's rule multiple times, I need to see that 0 over 0 is showing up every time before you do L'Hopital's rule. All right, let's just do 2 more here. Let's do example 4. Any questions so far? So if you look at this, we recognize this type of problem, right? This is a conjugate problem, which is fine, right? We can do conjugate method, but let's practice going through this L'Hopital's rule that we just learned. Okay. But it doesn't matter if we're doing conjugate or L'Hopital's rule, what's always the first step? Yeah, let's plug in, right? We don't want to assume anything until we gather some information. Okay, so if we plug 0 in, we get, what do we get? Okay, 0 over 0. So we know there's a hole in the graph. Normally you would go through conjugate, right? You would do multiply by square root of x plus 1, but we're gonna practice this other method. So we want to find the derivative, but before we find the derivative, what will make things easier with the numerator? How would you rewrite it to make it easier for power rule? Let's rewrite that radical, right? That radical can be rewritten as to the 1/2. Yeah. Okay. I want to find the derivative, so I'm just trying to get it to be easier for me to do that. So if you recognize this is going to be a chain rule problem, right? You got an outside portion and inside portion. So outside's derivative first. We do 1/2 parentheses to the negative 1/2. The inside stays intact. Multiplied by the inside's derivative. What's x plus 1's derivative? Just 1. Okay, so that takes care of my square root. Minus, what does 1 turn into? Right, still derivative, right? We're doing derivative of every term here, so all over 1. Yeah, so numerator and denominator gets, we find the derivative separately. And now we have our quote-unquote reduced version. What's our next step? Yeah, plug in the 0, right? See if that will get us a real number. If it does, then that's our answer. Okay, I'm bleeding into the space for example 5 here. 1 to the negative 1/2 is just 1. 1 times 1/2 is 1/2. Oh, that's a real number, so that's our limit. Okay. We would get the same answer if we went through the conjugate method. But there's going to come an instance where we're not going to have enough algebraic methods to handle this type of problem. And L'Hopital's rule is going to be the only way that we can get down to our answer. So for some problems, you can choose between 2 options. But down the road, L'Hopital's rule is going to be more robust. It can handle more types of problems. Okay, any questions? All right, got one more for us. Example 5. Limit as x approaches 3. Sorry, limit as x approaches 2. I'll rewrite this here. All right, first things first. It's our first step. Yeah, plug in the 2, right? So we plug in the 2. Okay, 0 over 4. Do we do L'Hopital's rule here? Is that an answer? Or is that a real number?
Yeah, 0.
Let's see, vertical asymptote looks a little bit different, right? Vertical asymptote would be like 4 over 0. Right. What's 0 over 4? 0, right? That's our answer. No L'Hopital's rule here. There's nothing more to do. So I want to bring this question up because if we misuse L'Hopital's rule, maybe you'll say it's 4/3 because you find the derivative. But that's not the case because we don't have a condition that matches L'Hopital's rule, right? We can't do L'Hopital's rule unless we get 0 over 0. If you skip that step, then you run into some trouble potentially. It's not 4/3.
Mr. Yang,
Yes.
I have a question on the last problem. Why did you put it over 1 instead of over 0?
Because x's derivative is 1.
Oh, because we were taking
Right?
derivatives.
Yeah, 1. If it's a constant, like 1 will go to 0, but a variable will have something left over.
Okay, thanks.
Yeah. Good. All right, any questions? All right, so tomorrow we're going to do the test review that I have on your website. I may make some changes to it today, but I think that's pretty much the version that I'm going to be going over. And then working on the key that I'm going to put on the website as well. If we don't get through all the review tomorrow, I'm going to spend some time Wednesday morning going over some more problems, but that will be recorded. And then Thursday will be your test. Okay. Over related rates, linear approximation, and L'Hopital's rule. All right, thanks everyone. Hope you guys have a great day.
Thank you, Mr. Yang.
Thanks, guys.